Hello everyone, my name is Dmitry Semenok. Today I will talk about superconducting in polyhydrides and their non-Fermi-liquid behavior. Now I'm representing HP Star Beijing, and a lot of my colleagues from Jilin University, China, Wuhao Chen, Xiaoli Huang, as well as people from Moscow. It's Ivan Troyan, Andrei Sadakov, Alex Sobolevsky, Vladimir Pudalov, and Tony Helm from Dresden, from Helmholtz-Zentrum Dresden-Rosendorf, and Stan Tozer from Florida University. They all participated in this project. As we all know, intensive studies of superhydrides began in 2015 when metallic sulfur hydride with very high critical temperature, around 200 kelvins, was discovered in Mainz, Germany by a group of Alex Drozdov and Mikhail Yeremets. And then 3 years later, two groups in the United States and in Germany almost at the same time discovered another unique compound. It's lanthanum H10, which superconducts below 250 kelvins. And mostly in previous years, people studied the question about the superconducting state in superhydrides. Yes, how small the resistance of superhydrides in the superconducting state is. This question is mostly was raised by George Hirsch. Scientists also investigated a lot the properties of resistance, this sharp resistance drop. But in my presentation, I will focus mostly on normal state behavior of polyhydride. Let me give you some examples of strange behavior of superhydrides in a normal state. The first picture shows behavior of cerium tetrahydride synthesized together with Wuhao Chen in Jilin University 2021. We see a quite big wave in the normal state of resistance of this hydride, which is definitely strange. The next example is hexagonal niobium H9 synthesized and investigated in 2020. We see that the normal state behavior of this hydride strongly deviates from Bloch-Grüneisen feed, which can be used for normal metals. And let's see the third picture. It's I took this picture from the publication of Katsuya Shimizu in Journal of Physical Society of Japan 2020, and we can look at the black curve. It's a compressed H2S at 150 GPa, and we see that during the heating cycle, warming cycle, the behavior of resistance of this H2S is not typical for metal, because the resistance decreases during increasing temperature. Here we see it's a typical behavior for semiconductors, but not for metals. And last one example I would like to show, it's a publication Maria Naga in Nature Physics in 2016, one of the first publications about the sulfur hydride. We can see that during decomposition, the behavior of this hydride in normal state changes, and at 111 GPa we see some upturn feature at the end of close to 250 kelvins, and this upturn feature should not exist in normal metals, and we can see that it's non-Fermi-liquid behavior. Okay, let me give you several additional examples. Let's look at the lanthanum H10, the figure 1 in the publication of Alex Drozdov and co-authors in Nature in 2019. And we can see the several temperature dependencies of resistance. 2 out of 4 of such resistance dependence have some features, downturn feature in the red curve, and this jump in the resistance showed by arrow. It's definitely not normal, definitely anomalous behavior of resistance. In the next publication, Wuhao Chen from Jilin University investigated the behavior of cerium H9 at 114 GPa. It's curves published in Physical Review Letters in 2021, and you can see there is a wave upturn feature here, which looks like a charge density wave. And definitely it deviates from the behavior of normal metal. Another example is the same compound at 88 GPa. The resistance transition is significantly lower, but we see that there is strong deviation from the Bloch-Grüneisen feed, from the Fermi-liquid model again, and even flattening of resistance curve at temperature around 100 kelvins. And we were able to reproduce this feature, this wave in the resistance curve in our Moscow laboratory. Yeah, we synthesized at 130 GPa the same compound, cerium H9, and measured the dependence of electrical resistivity on temperature. And you can see the same wave appeared in our experiment too. So it's a reproducible feature. So we need to think what can help us to explain this phenomena. What may be a reason of this phenomenon? So my question is, are charge density waves possible in hydrides? Okay, to answer this question, let's let's look at the temperature dependence of electrical resistance in different compounds. In layered, for example, layered niobium diselenite. And we can see on this plot that before the superconducting transition in this material, we really can observe in resistance, temperature dependence of resistance, the similar wave as we observed, the similar upturn feature as we observed in hydrides. Okay, let me give you another example. This is a publication from this year publication, 2022, and the afters hydrogenated titanium diselenite, also layered compound by hydrogen, and we can see how this charge density wave changes with time of hydrogenation, changes in dependence on hydrogen concentration in this compound. We see absolutely similar wave of electrical resistance in the normal state of this compound. Okay, and the third example is a series of sulfides such as niobium disulfide, tantalum disulfide, tantalum diselenite. We also can see in all of these compounds there is a kink in the electrical resistance or wave in electrical resistance in normal states of these compounds. Very similar to something we saw in hydrides in previous slides I showed. Okay, let's now look at similarity of hydrides to cuprate superconductors, and this is 2212 bismuth-based cuprate, where there is, as we know, there is a border between superconducting state and pseudo-gap phase, and we can cross this border by applying external pressure as it's shown on those three plots. Okay, without pressure, this compound in normal state demonstrates a Fermi-liquid-like behavior. In the normal state, behaves like a metal, so resistance increases along with increasing temperature. But when we applied pressure and pressurized this compound, we see that the behavior is close to the behavior of semiconductors, because the resistance decreases when we increase temperature. And this behavior is very similar to the behavior of H3S, which was published and demonstrated by Alex Drozdov in the first publication about sulfur hydride in Nature in 2015. We see that at high pressure, around 190 to 100 GPa, most part of the normal state resistance behaves as in normal metals, behaves as the Fermi-liquid theory predicts. But when we decrease the pressure, we see that the temperature coefficient of resistance changes its sign. And now at 107 GPa, we see that resistance decreases when the temperature increases. So it's opposite behavior than it should be in Fermi-liquid metals. So it's definitely H3S. It means in H3S we cannot use Fermi-liquid theory. We cannot explain the behavior in normal states of this compound using this Fermi-liquid theory. Definitely pseudo-gap phase, definitely strange metal. Okay, let me show another example we recently discovered. Together with my colleagues from Jilin University, we investigated the lanthanum cerium H9 ternary hydride. In one cell it demonstrates, as usual, superconducting transitions. In one of the cells we found that during decompression, temperature coefficient of electrical resistance also changes its sign. At high pressure it's positive, the sign is positive, but at low pressure during decompression it changes the sign and the sign is negative. So resistance decreases as in semiconductors when the temperature rises, and the dependencies are almost linear. If we apply to this situation the Boltzmann transport equation, at high temperatures, at relatively high temperatures, we can find this linear as usually dependence. As usually we can find this linear dependence, and the temperature coefficient of resistance will be proportional to electron phonon coupling coefficient. And in one certain point of pressure we expect to see a zero temperature coefficient, which means absence of electron phonon interaction and the zero electron phonon interaction strength. So the main conclusion from such situation is that superconductivity in hydride and the Fermi-liquid behavior in normal states, they are in principle incompatible. They are incompatible because superconductivity requires non-zero electron phonon interaction strength, and at the same time we cannot explain the absence temperature coefficient of resistance if it's only electron phonon scattering. So should be other mechanism of scattering. So it should be non-Fermi-liquid behavior of hydrides in a normal state. And here I would like to say a couple of words about Eugen Talantsev's publications. He published several papers in 2020-2022 and analyzed Uemura plot. He always underlined the fact that all compressed polyhydrides belong to an unconventional region in this plot. And this plot unambiguously identifies superhydrides and cuprates as the closest neighbors. Moreover, in 2021, Talantsev showed that careful analysis of the Fermi-liquid behavior of hydrides in normal state indicates some deviations that cannot be described in terms of pure electron phonon scattering. Recently, we studied lanthanum neodymium hydrides, and the paper about this system is published in Advanced Material in this year, 2022, and we found that kink in electrical resistance, this deviation, this anomaly in temperature dependence of electrical resistance, is accompanied by anomalies in magnetoresistance. Magnetoresistance changes sign above 200 kelvins, and at the same time, we saw anomalies in the behavior of Hall effect. It also changes its sign around 200 kelvins, exactly in the same place where this kink is observed. Considering all above mentioned, we can build qualitative phase diagram for polyhydrides. You can see it on my slide, and this qualitative phase diagram will consist of 4 different fields. And instead of level of doping, we can use pressure, which can be easily determined in experiment. At high pressures, hydrides will demonstrate Fermi-liquid behavior. At low pressures, we will see pseudo-gap phase where the temperature coefficient of electrical resistance is negative and the material behaves as a semiconductor. We saw it in H3S and we saw it in lanthanum cerium hydride. And between them, we will find a strange myth of non-Fermi-liquid behavior of hydrides, because in this field, superconductivity is incompatible with the behavior of normal state resistance. Okay, let me tell you what is probably behind this qualitative phase diagram for hydrides. The possible mechanism was proposed in a paper of Yuzbashyan and Altschuler, published in this year in Physical Review B. They investigated the upper limit for electron-phonon interaction strength within the Migdal-Eliashberg theory of superconductivity. They found that if this parameter of electron-phonon interaction is over some critical value, the heat capacity of superconducting materials will be negative, and the superconducting state in this case will not be stable and will turn to insulating state. It's something we observed in hydrides. When we decrease the pressure, we usually go to molecular polyhydride. It may be semiconductor or strange metal, and after that, this molecular polyhydride decomposes with formation of 2 separate phases. The first is again the metallic and maybe even superconducting phase, but with lower hydrogen content, and the second phase is insulator. It's a molecular hydrogen. We can speculate that due to very high amplitude of hydrogen vibration in the polyhydrides, at low pressures they may form some kind of excited hydrogen molecules, which will exist a short time and also participate in the process of electron scattering and will contribute to electrical resistance of material. Okay, and let me turn now to the main topic of my presentation. It's formation of tin hydrides at high pressure, about 170 to 110 GPa. On the panel A, you can see compression of pure tin. You see mostly it's BCC and a small impurity of hexagonal phase of tin. After that, we compress at stannane. It's unstable gas. We load it in the diamond anvil cell, and after that compressed to 180 GPa. And you see the main product of compression is FCC tin H4 with the same hydrogen content as initial compound. This same product can be also synthesized using tin and molecular hydrogen loaded together, and as well we can do it by loading ammonium boron, and also the main product of the reaction is tin H4. In addition to the main product tin H4, we have synthesized several new tin hydrides, including higher polyhydride C2M tin H14, which was predicted using the theoretical methods. On the panel A and on the panel D, you can see the experimental X-ray diffraction pattern for this compound and the theoretically predicted one. You can see the correspondence between the theory and experiment is quite good, and theoretically predicted unit cell parameters and volume are in quite good agreement with experimental ones. As well, we also synthesized several lower hydrides such as SnH2 and Sn2H3. Okay, and after that, we investigated transport properties of SnH4. And first of all, we noticed that this compound demonstrated a superconducting transition at about 72 kelvins, but at temperature around 120 kelvins, we can see a kink in the temperature dependence of electrical resistance. When we investigated the behavior of this compound in external magnetic field, we found that actually the upper critical field is linear, and this is serious deviation from the WHH model, which is commonly used for conventional superconductors. There is unusual upturn feature, unusual increase in the electrical resistance when superconductivity is suppressed by a strong magnetic field. You can see it here on this diagram. And finally, we investigated critical currents. Results show that the critical current in this compound is pretty small. On this slide, I would like to one more time underline similarity between the behavior of tin hydride and cuprates. On the left side, you can see temperature dependence of electrical resistance for cuprate. Red curve shows behavior of electrical resistance in high magnetic field when the superconducting transition is already suppressed. We see that electrical resistance grows at low temperatures. And absolutely similar behavior we see in the SnH4. The SnH4, when we suppress superconducting transition by high magnetic field, about 16 Tesla or more, we see the rise of electrical resistance at low temperatures. We also studied transport properties of tin tetrahydride in high pulsed magnetic fields up to 65 Tesla. And we found that linear magnetic resistance dominates in this compound. Only in very narrow area of magnetic fields below 10 Tesla we can use parabolic field to describe the behavior of magnetic resistance. We also measured Hall effect in this compound at two temperatures, at 75 and 100 kelvins, and I found that the Hall effect is pretty small. In conclusion, I would like to underline that behavior of many hydrides in a normal state is anomalous. We need to seriously consider the possibility of formation of charge density waves, spin density waves, pseudo-gap, and strange metal phases in polyhydrides under pressure. And Fermi-liquid theory is inconsistent with conventional superconductivity in polyhydrides and cannot explain their normal state behavior at low pressures. Thank you very much.